اوكي، بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. First good news is that this is the last lecture, topic number 1. So there will be no more mathematical abstract stuff. We're going to be starting doing the calculations, inshallah, from next time. And I'll ask you at the end of the course whether you want to remove that topic or not. And we'll see. Okay, so you will decide yourselves whether this is actually important to understand what comes or not. So far, this has been, I know, a very painful journey. Today will even be more painful. So far, what we did in the last 5 lectures, we did not do any differential geometry, believe it or not. Okay, so this was all linear algebra, basics of set theory, and talk about group theory. This is very basic mathematics stuff. If you already knew it, then you find, okay, we did not really say anything, okay, substantial there. It was just we were agreeing on the notation, how we use. But if you already had a proper mathematical background, which I expect you don't, okay, because you're all mostly engineers, so that's completely normal. This is why we needed to have the last 5 lectures. Today's lecture is only differential geometry. In the book that we're going to be referencing to, they have this. They actually have a very short version of differential geometry in 80 pages. Okay, so we'll not be able to cover everything. Okay, I know that there is. I'll give you some online lectures if you want to watch it. It's a 10 credit hour course on differential geometry. So good luck. Okay, so you can, if you want, you can dive in. So there's no way I can tell you everything about differential geometry. What I'll try to do here is that I'll try to mention the intuition. What do we mean by, okay, why do we need the differential geometric stuff? What the main 2 objects that we're going to be using now on are the manifolds and the Lie groups. Okay, so these are you only need to understand the intuition of what this is, because the mathematical formulation of it is actually very heavy, okay, to do it properly. So first, why do we need to talk about the differential structure? So let's go a little bit back. So we looked at Rn from now on in the previous lectures. You saw Rn as a set, which is simply the Cartesian product of R with itself n times. And you thought of these are just n tuples. That's it. Could you do anything with these n tuples? The answer is no. You cannot do anything. You cannot add them together to do anything. You cannot look at how if this is a vector. You cannot even call it a vector. It's just a set. If you want to call it a vector, you needed to introduce what's known as the field, and then we needed to have this vector addition and the scalar multiplication operations, and all of them together, if they satisfy some conditions, we call it a vector space over a field. And with that, you can do stuff. You can start talking about vectors. You can start talking about adding 2 vectors to each other. You can start talking about the scaling the vector and making it smaller or bigger and so on. So you can start talking about directions. But in dynamical systems, that's not enough. We don't just talk about the vectors. We start also talking about the rate of change of these vectors, so that you can describe a differential equation of, it's not here, it will be later, but you need to describe how a vector changes with time. And you need to describe a curve in this vector space. And you need to start to do calculus, which is differentiation and integration, and start to look at limits and stuff like this. So this is the basic mathematics that you all know. And all of this, in order to do this analysis, we need to have what's known as a differentiable structure. Okay? It's easier to think about it, to work with it, than really to formulate it properly what the differentiable structure is. But if you take a set M and you give it this differentiable structure, then you just call this a differentiable manifold. So the Rn that you're used to, which is to describe maybe like x dot is equal to ax plus bu, where x here lives in Rn. So this is the Rn that you're used to, and you need to describe differentiation and addition, and to work with it. This is actually you're thinking about Rn as a differentiable manifold, not just as a set and not as a vector space. We're going to be formulating how this differentiable structure looks like in Rn. So now we're in Rn, the one that you're used to, and you should be familiar with all of this, but okay, since you have a broad audience here, and some people might not be familiar with this, or some people might even not remember it, we're just gonna build it step by step. So in mathematical analysis, if I give you some function and I tell you, how smooth is this function, then the smoothness is just a property of the function, and it is simply how many continuous derivatives can you calculate for that function. If you have a function, okay, that goes from R to R, we're going to be looking at the simplest case. I have just one function that goes from R to R. This function might not even be defined on all R. It can be just in some interval. Okay? It can be just some open or some closed, some open interval from R to R. Then we have the function f is said to be of class C0 if it's continuous. We say if it's class C1 if its derivative exists, and both the f and the derivative, so f dot or f prime, are continuous on this interval. Class CK if it's continuous and its first derivative exists and its first derivative is continuous, and its kth up until the kth derivative it exists, and also the kth derivative is continuous. And if you have this all the time, if you have it up until infinity, we call this a C infinity function, okay? Or simply just a smooth function. So whenever you say a smooth function, you already are talking about that if I take the differentiation of this function many times, as much as I want, you always get a continuous function.
What differentiation as a map?
No, we'll not go there. No.
Is it possible? Is it something?
I'll not answer that question because it will divert. So visually, you know what I'm talking about. So visually, if I tell you this is a function, okay, it's a C0 function. Why is that? It's continuous. It doesn't have any jumps. What about this function? It's not continuous. It's not C0. It's not of a class C0. Why? Because it's not defined here at the 0. It actually has a jump. So if you look at the x equal to 0 of this function, this is actually the function 1 over x. It has some number. It has a value here and a value here, but at the value x equal to 0, it's not defined. Okay? And it's not just even not defined. It's even you don't even know it's positive infinity or negative infinity. Okay. So this is an example of the C0, and of course, if this functions are how many functions do we have? We have an infinite number of functions on R in general. So can you think of any function that's that's C1? Yeah, you can always cook them up. You can C2 and C3 up to infinite functions and so on and so forth. For example, a sine wave is simply it's an infinity, right? You can take if I take a differentiation 1, I get the cosine. If I take a differentiation again, I get the sine again with some, and so on and so forth. Actually, this function itself is even a stronger form of differentiability. It's actually called an analytic function, but let's not go there. Can we extend this definition to Rn, to function on Rn? So instead of having just from R to R, a function from Rn to R. Okay? Yes, you can do exactly the same by simply looking at what you call the partial derivative. Okay? I take the partial derivative of this with respect to the first variable and the second variable and so on. So this is okay. It easily extends to functions on Rn, and this is okay. You've seen this somewhere, okay, along your mathematical journey. And this is again how you would visualize it in R2. So this is an example of a C0 function in R2. Okay, it's only C0 because if you come to the point here 0, 0, and you try to take the differentiation, you'll find that you have some jump, right? You can see it here from that we're going smooth. Okay, we're going continuously, and up to some point the differentiation becomes very big. It instantaneously changes. So this is not C1, it's just a C0 function. And this is not even a C0 function because the same point it has this discontinuity, okay, along R2. You can extend this to Rn, but you cannot visualize it anymore. Okay. So what is the formal way of doing? So this is only with figures. Okay, with graphs, you can plot the function and you can see whether it's really continuous or not. But how do actually mathematicians do it? By analysis, by pen and paper. This is where you need to talk about what's known as a topology. Topology is a very nasty subject in mathematics. Okay, I'll not go there. I'll not even come near it. But simply, if you take a set M and you start to want to talk about the continuity of functions on this set M, okay, just exactly like we did now with Rn, then you need to actually make it into a topological manifold. And what makes a set into a topological manifold? You're going to give it this extra structure, which is something called a topology. The topology is a set of sets. So don't go there. It's just a set of sets. You remember how we made a vector space, how we made a set into a vector space? We give it operations, right? So we had these operations. But now the extra structure is actually another set that we call it the set of all subsets of M, of all open subsets of M. Okay, so and they need to satisfy some certain conditions, very, again, some very heavy mathematics. In the end, if you take this M and this curly O, we call both this pair, we call it a topological manifold. You've had this all along in Rn, okay? And what you actually were you always using is something called the standard topology there. Have you ever heard about, if you remember a long time ago when you took, analysis or calculus on Rn, something about if you have a ball, right? If you have some ball, open subset of ball, and you need to have, points that are near each other, they need to satisfy that, if you take the ball and you make it as small enough, the point still remains there, something like this. So even you don't know what a topology on Rn is, so that's good. Okay, so if you really know, you really need to go back and you really need to visit that stuff. You need to look at the standard topology from the beginning, but you're always assuming it. You're always assuming we have that. So that's the point of this discussion. The idea, if you have a differential equation, okay, on Rn, so P lives in Rn, and P dot is some function of P. So I have some function that describes how P evolves with time. This is typical, okay, when you have, want to describe dynamical systems. And for example, like a motion of a point, or like how a configuration of a robot, and so on and so forth. So this differential equation, in order to actually write this equation, you need to have this topology, and you are assuming here Rn is not just a set, it's not just a vector space, but it's even more than that. It's a topological, it's a differentiable manifold, so that you can take differentiations and so on. So this is all of the math that's under the hood that you always assume Rn has, and so on and so forth. If we want to do analysis on a manifold, how can we extend these concepts to this, okay, generic case where this manifold is not Euclidean? Okay, so Rn, if you take Rn, the set Rn, and you give it the standard topology, you get a manifold, but it's like the nicest manifold that you can always have, which is Rn we call it just the Euclidean manifold, okay, or the Euclidean space. And you can do all of the stuff that you're used to. How can we extend this to stuff that is not Euclidean? Okay, that's the whole idea of this discussion. I'm gonna leave math completely. Let's go to something very visual, something very, intuitive, okay? And hopefully, okay, it will make sense to you. You all know what the atlas of the world is? When I just say the word atlas of the world, what comes to your mind? When I say an atlas, if just an atlas, what comes to your mind? No? What's an atlas? Okay, your dad had a book called an atlas. So what, you remember if you open that book, what you found there? Maps. Exactly. Maps of what? Of the world, exactly. Did you have one map? Many maps, okay? 100 or 200, just some number, depending on how thick the book is, okay? That's exactly the whole idea. So the globe, okay, Earth, okay, our beloved Earth, is actually an example of a two-dimensional non-Euclidean space. Okay. So it consists of point along a sphere. Okay, assume it's just a sphere. I don't know if you're a flat earther. Okay, if not, okay, then this doesn't make sense to you. You think that it's really R2. Okay, I assume no one is there. So this map, so it's a two-dimensional non-Euclidean space. It's a curved ball, right? And then if you want to describe it with an atlas, if you open this atlas, what you're going to find inside, exactly, you're going to find R2 maps, exactly. You're going to find a lot of R2 maps. R2 is what here in this context? It's just a paper, right? It's just a finite, paper, and inside of it, you're going to find some map of the globe.
For flat, we call it R2.
We introduced it before, it was S2. The set S2 that we introduced before, which was the triplet, okay, it was a subset of R3. That's why you can visualize it. It's a subset of R3 that satisfies when you take x squared plus y squared plus z squared, you get some constant square. Okay. We introduced it earlier to be actually equal to 1, and we call this the unit sphere. But here, Earth is actually it's not just some unit. It just has some length. Okay. Any questions so far? Okay. So an atlas of the Earth is just a collection of charts. Each chart maps a local region. This is very important. You don't have one big map for all of Earth. You just have, inside of at least the atlas, you just have a little part of the Earth, and you have it, okay, in a piece of paper. Make sense? Intuitive, no math. Okay. So I'll take an example, okay, of two regions. Okay, one region, okay, of Earth that contains Egypt, and another one that contains Saudi Arabia. Okay. And if you open the atlas, you'll find, okay, the chart that has Egypt looks like this, and the chart that has Saudi Arabia looks like this. Make sense? A chart of Earth, okay, consists of the pairs. We're going to be calling each chart a pair U and a map phi, where U is an open subset of the sphere of Earth, and phi is a map from U to R2. And it's a continuous map. Very good question. Do you know what an open map is? Or open set, sorry. What does an open set mean? That the boundary is not taken into account. Okay, so if you look at this, for example, the boundary itself is not part of here. It's not actually part. You can zoom as much as you can. You're not going to find there's a boundary. This is what an open set means. Just like when you have an R, when you say what an open, for example, if I take the open set from 0 to 1, what does that mean? Or not include, exactly. So the boundary is not included. That's what an open set means. The reason why we only look at open stuff is because of the topology. So just, link that together, and, maybe if you get interested, you look at it later on. So what is a chart? If I tell you just the question, what is a chart? No?
Subset or the linearized part of...
Don't use any words we do not use. No linearized. So what's the chart? No. It's a pair of a subset of the map of the manifold, a subset of Earth of S2, and the map that takes you from that subset to R2. So you see here, the region, okay, the curved region that has, if you take the globe and if you only copy, the region that has Egypt, this one that's in red, okay, then we call this the subset. It's not the whole set. It's just only this part, this circle. And this the green one is that has Saudi Arabia. And the map phi, okay, will take this piece of land and we'll put it on a paper like this in R2. So you see, this is a subset of R2, and phi of this, okay, is what? Does anyone remember what we call this name? What was phi of this subset? We call this the image, you remember? The image of this set, of this domain under the map, okay, is given by this, and it's a subset of R2. It's not all R2, it's just a subset. That's why we draw it, like this. And we have the same here. Any question so far? If we do this again and again and again for all, patches, over the globe, you can build what's known as an atlas. So what is the atlas? The atlas will be defined as the set of all charts.
Why can't you take it for the whole globe?
Very good question. Well, I'll keep that later. So the question was, why can't we have one chart for the whole globe? Very good question. Which means what? You can never do that. You can never do that. I'll give you 100 riyals, even more. If you can go to a globe and take it, and destroy the paper that actually it was drawn on, and try to draw it in only one paper. If you do that, what does that mean? It means actually that Earth is not a globe. This is R2. And this is exactly what we mean. So why can't we just have one map that covers the whole Earth? Simply because it's not R2. It's not Rn. This is exactly what we mean by Rn. If you can have one chart that covers the whole, set we were talking about, in this case, this is the manifold. We did not define what a manifold is, but this is exactly what the manifold is in this case. It's the S2. If you can have one chart that covers the whole manifold, then actually the manifold is simply Rn. Okay, in that case. In this case, it's R2. So because you cannot find one chart that covers the whole manifold, it's actually not Rn. It's not.
Can we know this chart at the end? It is flat as we see. It is not nonlinear or curvy.
The map itself is a piece of paper, so it's always straight.
How can we decide these limits, or how can we know if perhaps we can take a chart from apart?
Yeah.
But actually it is curvy,
This one is curved, right? Absolutely. This is curved. Very good question. This is why, this is exactly what we're going to be talking about. I'll give an example in a bit, okay, to make that clear. Question?
So I think it's related to this question. We decided that the atlas is a collection of all charts.
Of all charts, yes.
So let's say these charts are 1,000 charts.
Okay.
So the atlas can also be equal to only 100 charts. So 100 charts equal 1,000.
That's right. Yeah, you can have that.
Figure?
It doesn't matter. There is no such thing as the dimension there. You can just have as many as you want. In the end, that's the whole idea. If you want to have a complete atlas, then simply, when you take all of the charts and you take the union of them, this is a notation for the union of all the subsets UI. So I had here UE and US that had only Egypt and Saudi Arabia, but I should have all, more patches, more and more. Each one of them is curved. So when you take the union of them, what do you get? You get the initial globe that we started with. That's the only condition for this to be an atlas. You can have I as many as you want. And here there's just a notation, a new notation we never used before, which is whenever I say I lives in A here is simply the index set. I can have here I, for example, in this case, I, is E and S. Okay, but I can have 1, 2, and 3, and 4 up to 100 or 1,000 depending on what you have. So this is this is a general way to say that I is as much as you want it to be. There is no limit there. Okay. Yes. Yes, say. That's right. That means that the Earth itself is actually, because this part, this means that you have a map from all of S2 to R2, which means it is okay that that actually R2 and S2 they are isomorphic to each other in some sense. Okay. So the question that I think there was a question I did not answer, which was, could you remind me? Yeah. Okay. About the distance. Yeah. So here, this is R2. If I move from here to here in a straight line, how do you visualize it here? It will be a curved line. Because actually this chart, okay, is not a linear map. The linear map, you remember how we used linear maps? We said linear map is between what and what? Vector space and a vector space. This is the only thing that preserves distances and length and stuff like this. But this is not the case. This is just, you take a patch and things will be messy here. And this is why distance is here. Distance is something you can only do with vector spaces, which is even not even something we discussed at all. If I tell you the distance of a vector, how do you calculate it? You take the norm of it. How do you calculate the norm? You take the inner product of the vector with itself. Did we ever talk about inner products here? You remember in last lecture, I told you that there is an extra structure to have an inner product. It's actually to use distances. And the same for angles. That's why in the charts, distance and angles are completely messed up. And this is why if you take the whole globe and you put it in one chart, the famous one that you all know, angles and distances, they completely mess up. Africa looks exactly the same as Greenland. So when you watch the news and they want to take Greenland, you actually, if you look at it as a patch, it's actually as small as this. It's actually much smaller than actually the whole of Africa. Okay, so Africa is much bigger than actually what it appears on the famous map that you all have in your mind of the globe. So distances are completely messed up in that case. So we still have overlap regions here. This is very important. If I have some overlap region here, they always need to be compatible to each other. So if I look at this region here in this map and in this region here in this map, which is actually a compatible one, okay, these have to be compatible with each other, okay, depending on how the map looks like. So this is another condition that we need to always make sure. Compatibility itself, what does it mean? Okay, we're going to be looking at it mathematically, but you get the point, right? So distances here, they make sense to distances here, okay?
Maybe like the current should be same.
No, you should be able to relate one to the other. That's the idea. Okay, if you look at some distance here, for example, if you look at the width of the Red Sea, okay, or I don't even know, yeah, that's the Red Sea in this case. If you look at the width of the Red Sea, it should make sense whether you calculate it from here or here. You actually see it already. They're not the same size, right? I think so. Yeah, this is much smaller than here. So, if you calculate how long of it, give it as a homework to, your nephew or to your son, and you'll be like, oh my God, this is different. So how can I trust the map? But actually, they should be compatible. You should be able to transform one to the other if you know how the maps are, done. This whole stuff of how you actually build maps, there's a whole specialization by itself. I think it has a name of, what's the name? Cartography or something like this. I'm not even remember. But this is actually a science by itself. They have to be compatible. Charts, they need to be compatible in the overlap region.
Chart, but at the end it's approximation chart. It's because it is not.
It's a chart. This is the definition of the chart. There is no approximation here.
For example, preserve this distance, so it's approximation to
No, there is no approximation here at all. The chart itself, you can make it bigger or smaller. You can play around with it. This is the definition of the chart itself.
So there is no compatibility
Between in the overlap region. So you're talking about distances here, or with respect to the initial manifold we're talking about?
If we see this, this not compatibility, so this is not charts.
No, the compatibility is built in it for it to be a valid chart. That's the thing. So they have to be compatible. That's the whole idea. Okay. So this was just the introduction part. Now let's look at the proper way of discussing, these differentiable manifolds. The fundamental object in differential geometry is what's known as a differentiable manifold. Okay, so this is the basic object. This is the new structure we're going to be talking about now. So now we know about sets, groups, vector spaces. This is the new object we're going to be talking about, which is a differentiable manifold. Intuitively, you can understand what it is. An n-dimensional manifold is a set that locally looks like an open subset of Euclidean space Rn. Locally looks like. What does the Earth locally look like? It's flat. It's R2. What does it mean? It is exactly what we have in this, go up and, in an open desert and stand there. What do you see? With your eyes. Flat area. So in your place, if you look around you, you feel as if you're just living on a flat area and just on a plane. That's exactly what a manifold means. It locally looks like that. But if you take an airplane and you look from above, you see actually there is a curvature. Okay. So that's what it locally looks like. Intuitively, this is what it is.
For example, if this is in a dimensional manifold SC2, it lives in two-dimensional. But
it is two-dimensional, yes.
R3.
No, it's locally R2. I'll give an example. I'll give an example. I'll give an example. No, I'll give an example now. So here, the circle is an example of a one-dimensional manifold. Okay. Now think you're only living on the circle. So this is where you live. The same also for the sphere. You're only living on the sphere. So you can only move, if I stand here, I can only move sideways. I cannot go up. So imagine, you don't think that you can take an airplane and fly up. If you're living on a sphere, you're always there, just like an ant. Imagine that you have an ant here. So is it 2D or 3D? If you can never leave the sphere. 2D. Okay. The torus is another example. The donut, donut, Dunkin' Donuts. So now I know you're hungry now. Okay, but if you're an ant that lives on a Dunkin' Donuts donut, okay, you can never leave the sphere. You can never leave the torus. It's another shape, but this is another 2D dimension, the two-dimensional manifold. Space-time is an example of 4D dimensional manifold. Exactly. What about in robotics? If you look at the configuration space of most mechanical systems, which are, the basis of what we have in robotics, just a pendulum, you'll find actually the pendulum is simply the circle, which is, as I said, just a one-dimensional manifold. If you look at an n degree of freedom manipulator, the configuration, assuming that all of the joints are, revolute joints and they can revolute as much as they can, you actually will have what's known as an n-dimensional torus, which is a manifold also. if you have a planar mobile robot, it's just a simple, robot with 2 wheels or, differential drive or anything. So, no, it's an n-dimensional torus. It's a donut. It's an n-dimensional donut. No, we'll have one lecture. We're gonna be looking at it, inshallah, and I can give you some references to look at it in more details. There are some nice stuff on the internet for that. A planar mobile robot lives in a configuration manifold that's a 3-dimensional one. A multi-rotor air vehicle, just a drone, quad rotor or any just flying rigid body, is actually a 6-dimensional manifold. If you have a robot arm on a drone flying or underwater, you actually have SE3 times Tn. You have a 6 plus n dimensional manifold. Okay. None of these is Rn. Okay, and this is the 6 weeks later. So actually 6 lectures later, I started the first lecture by this slide, and I told you if you only know Rn, you cannot do a lot of stuff, okay, in real life.
Can you explain a little bit the SCE and how it played out?
No, of course not, because that's the whole course. Okay. Yes.
For example, some manifold or something, it lives in a dimensional or whatever.
No. You're using notation. You're using notation we never use. When you say a manifold lives in some n dimension, what does that mean?
You mentioned that it looks locally in Rn.
That's right.
So this Rn could be this Rn with everything in the manifold. This n could
No. It's only locally how it looks like. It changes from space to space.
In this
On the manifold. Exactly. It will change from space to space. These are different spaces, and we're going to come to that in the end of the lecture. So, a differentiable manifold is different from what a vector space is and what a group is. So, in general, a manifold, usually we're going to have this, curved space that to describe this is a manifold. Whenever I say a point here, this is a point on the manifold. This is another point, and this is just, a curve that connects both to each other. We're going to see this picture again and again, okay? Because this is an abstract picture. It's not. I draw it as if it's a 2D surface, but we're thinking about it, as an ND surface, an n-dimensional manifold from now on. But it will help us visualize some stuff abstractly. A manifold in general, could not have a vector space structure, which means that if I take 2 points on the manifold and I sum them together, or I take the difference between them, it might not be defined. And if I take the point and I multiply it by some scalar, it might also not be defined. So these are the typical operations that we would have if you had a vector space structure, right? You can always take the sum or the difference between any vectors. You cannot do that in general on a manifold. The same also for a group. A manifold does not necessarily has a group structure, which means that on this manifold, there could be no binary operation, which means that if I take 2 points and I want to do something to them together and get another element of the M, could not be defined. I could not have any identity element, a unique one. So, for example, where is the element, the identity element, could not be there. And it could not even, if I don't have, these two, naturally follows that I don't even have an inverse. So what is the inverse of Paris? So Paris is a point, right? On the manifold, on Earth. What is the inverse of it? If you add Paris to Egypt, what do you get? You don't get a little Curacao or something. It doesn't make any sense. So that's exactly what I mean here. So points on the manifold, you know what they are. You have all of these cities. They're connecting them together doesn't make any sense. Connecting them together makes sense. You can move from one to the other. But if I add or subtract or multiply, all of this fails. No. What is Paris plus Egypt? Paris plus Egypt. Nothing, exactly, not defined. That's what I mean. What is Paris multiplied by Egypt? They are both points on the manifold, exactly. But they're not defined. It doesn't make any sense. There are some special cases of manifolds that are very nice because they have a group structure. And these we call them Lie groups. So Lie actually is the name of Sophus Lie. So actually I think is a French mathematician. Okay, look that up. Don't quote me on that. But he was a mathematician for sure. But he was very famous and he did a lot of work on, these kind of structures, which are a manifold that is also a group. Okay? These are very special and they appear a lot in the robotics. So now let's see how much time we have. Okay. These are some slides. I'll leave them for you to read at home because they are very much in the line that we said, that about, about taking Earth and looking at the atlas. This is exactly the same language you need to actually describe mathematically what a manifold is. So I'll just go quickly over them. That if you want to have this, say what a CK differentiable manifold is, three things: is an set M, a topology with it, and an atlas. Where both of these together, they are called what is a topological manifold. You don't even know what that is, but I need to formally say it. And A is a CK atlas for M. What does that mean? A CK atlas is simply a collection of all charts that cover the entire manifold while satisfying certain overlap conditions. That's exactly the intuition I gave you from the atlas of the world. And if you have this CK differentiable structure on M, we can talk about curves on the manifolds, maps between manifolds, and differentiability maps, and so on. And this is what we're going to be doing on the board in a bit. CK, you came late? You weren't there from the beginning. What was CK? The differentiability class of the functions. Okay, what we discussed in Rn. Yeah, exactly. So a chart for a manifold is simply a pair where you take a subset of the manifold. It's an open subset of the manifold. And related to your question, what does an open mean? It actually has something to do with the topology. So that's why I cannot answer your question unless I tell you what the topology is. And phi is a map that goes from this open subset to Rn, where phi of Rn is an open subset of Rn. So you're going to find the word open, open, open again because it's related to this idea of topology. And this is exactly the same picture that you have here. So if I take a region of the manifold abstractly, okay, and I have a map, I will go to this, orange region. If I have this green, okay, patch of the manifold and I map with the other map, with the other chart, I have this other region and I can always go back and forth, especially in the overlap between both. Okay.
I define it in a way where there's no overlap and I just keep all of these intricacies of manifolds.
Can you define? Then you need to go into mathematical theories, and I cannot answer them. I don't know. In general, you cannot. Okay, but that's my simple answer to that. A CK atlas is simply the collection of all of the pairs of all of the charts that we have, such that when you take the union of all of these subsets, you get the initial manifold. And if you look at in any intersection where there is an actual overlap, you find that this overlap map is of class CK. And this is why we need the CK notion, okay? Because these overlap, these compatibility maps, these compatibility conditions, they need to be differentiable. This is the idea of being compatible, being able to go from one to the other.
All the subsets that don't intersect with each other, like in an atlas, like Egypt and the Greece.
Absolutely, that's right. Yeah, that's right. Exactly. And that's why you don't need to talk about compatibility. Yeah. Have you ever seen someone that's looking at the map of Egypt and the map of, South Africa and trying to compare anything between them? There's no overlap. That's why you can only do this compatibility in the overlap region. This is, there's a lot of heavy notation here, but if you look at it with the intuition that we discussed, it will all be clear. This is exactly the same intuition that the same definition you're gonna find, in the textbook. So it's really, that's it. And I know there's not a lot of math, but this is precisely, okay, the definition of what a manifold is. Now let's go to the board and start to introduce more notations, okay? Just to introduce you to some terminology we're going to be using a lot in the coming weeks, inshallah. Let's see. Okay. So first, we're going to be defining what's known as a curve on the manifold. So what is a curve on a manifold? If you can imagine that the manifold is this picture we're going to be drawing again and again. So this is the manifold M, and this is some point X, a curve, okay, gamma, So this is what I just drew intuitively. Okay, it's just what we call a curve. It's always on the manifold, by the way. So it's, you know, any point at that curve is actually on the manifold. We never go up or down or, you know, so the manifold is all that there it is, okay? So gamma is called a curve if it is a map between some interval. Okay? This interval can be from 0 to 1. For example, let's say this is the initial point, 0. So this is the parameter, let's call the parameter, I don't know, like t equal to 0, and this is t equal to 1. Okay? Then you would call this a curve. So you go from some interval from R to the manifold M. Okay? So if I take any t here, where do I go? To gamma of t. What is gamma of t? A point on M. Exactly. So gamma of t is any point on M. So if this point is called x, then here, for example, in this figure, then gamma of 0 is equal to x in this figure right there. This is exactly what it means. So for example, let's say that this is x1 and this is x2. These are the points themselves. So gamma of 0 is equal to x1 and gamma of 1 is equal to x2. And of course, anything in between. The 0 and 1 are not exclusive. I can call them A, B, you know, 0, nothing matters there. This is just what's called a curve. It's a parameter of the curve. It's called a parameter of the curve. Why I call it t? Is it related to time? It could be. T itself is the parameter of the curve. Exactly. So this is what a curve is. Make sense? Easy definition. Okay, there's nothing, you know, complicated there. Now let's look at functions on the manifold. I'll give you another definition now of a function on the manifold. This will be a very important definition because we're going to have it later again and again, especially when we start talking about the control part. So a function f that takes you from M to R, okay, is just a function on the manifold. That's it. Full stop. Can we say anything about this function? Can we say it's continuous, or I mean it's class C0 or class C1 or CK or C infinity? We don't have any way to do that, right? It's not identified exactly. We don't have any tools to do that, except through what? Except through the charts, exactly. So if I look at F, I'm going to draw a commutative diagram. You remember what a commutative diagram was? So F takes you from what to what? From R to M, right? M to R, sorry. Yeah, you're absolutely right. So from M to R. And what does, if I look at M, but only a subset of it. So let's say I look at a subset U of M. Where can I go? With a chart phi, where should I go? Rn in general. Okay. So here we mean that M is an n-dimensional manifold. Okay. So the dimension of M is equal to n. We never talked about actually what the dimension is. You remember what we did with vector spaces? Intuitively you know what it is, but formally to define it, we need to introduce something else. Hopefully we're gonna get the time today. But intuitively you know what it means. Okay. So phi goes from M from this open subset to Rn. And now this map how is it defined? Can anyone remember? Yeah, composition exactly of what and what? Of n, f and when you say a chart, you actually mean these two together.
Is the inverse Rn.
Exactly. There's no times. Composed, so it's F composed with phi inverse. So phi takes you from U to Rn. What does phi inverse take you from? From here to here. And then the F will take you afterwards from here to R. So this is exactly the curve that you the diagram you have here. Make sense? What is F inverse? First of all, F inverse. So F composed with phi inverse actually has a name. It's called the local representative of F in the chart U phi. This is the name of it. Make sense? As a definition? Is it clear? Take your time. If it's not clear, let's repeat it. Yes. In this way, yes. So F is the map from M to R. Okay.
Why we said the map from M to R?
That's what a function on the manifold is. A function that eats a point on the manifold and gives you a real number. It's a very important object. We're going to be using it later. That's why this is the formal definition. Okay, that's right. Sorry? Let's see. Yeah, but that's it. This is, no, I said that. I said inverse. I said phi inverse circ F. But there's something else. That's not what we're talking about. We only want to have this map. So this is the definition of it. Okay. So this map is simply the local representative of it. Where does this map take you from? Where does it go from where to where? From Rn to R. Do you know how to describe the differentiability of a map that goes from Rn to R? This is what we discussed at the beginning of the lecture. From the partial derivative stuff. You remember we had the R to R, and then we extended it from Rn to R. So this is a map from Rn to R. So if we want to say that F phi inverse takes you from Rn to M, and F takes you from M to R. So this is a map from Rn to R. Both of them together. Remember what we said about this? It's a new map. All of this is just the name of one map. Let's call it F sub phi. Whatever, it doesn't matter. Okay? But all of this is just one map. It's the definition of one map. Okay? So this is a map that takes you from Rn to R, and we know there how to describe differentiability. Okay? And thus you can say that F is actually of class CK if its local representative is of class CK. But not in one chart, it has to be in all of the charts. So you have to always check in all of chart this is the case. So here we only did it in one chart, okay, and in one subset of M. We have to check this in all charts around the manifold.
CK is for the F or the manifold set.
No. CK is, you only talk about class CK for functions. Okay. M itself is actually a differentiable manifold if the atlas itself has all of these maps, all of the maps to be actually of C class CK. Exactly. Usually what happens, so because we're engineers, usually what we do is that everything is smooth. So K is always infinity, which means that you take differentiation, nothing happens. You don't care about what happens. If you have something that's CK, okay, in real life, there are actually very prominent applications, but we're not going to be going there. Sometimes if I take differentiation of a CK function, what do I get? A CK minus 1. You always lose differentiability. Okay, so this is something you always need to take into account if you have a CK option. But if you want to do, you just to at least as a starter, assume everything is infinity. So you're gonna find always the notion that we have a smooth manifold, we have a smooth function, which means that everything is just infinitely differentiable.
You assume that there is a bijective map between the manifold and Rn.
This is how the chart is defined. It's actually, it should be bijective. By the way, it's not between M. It's only between the U. From U to Rn, you can go back and forth. If you go back to the intuitive example, if you open the chart that has Egypt, right, and you look at the globe, you're going to find always the map goes back and forth. Every point here on this piece of paper corresponds to an actual point there. You don't have Alexandria and Cairo mapped to the same point there. And always back and forth, right?
Okay, for example, if I have يعني messy curve, يعني if I take some projection.
We're not talking about points. You remember what a bijective map is? Only between sets. So you have only abstract points. There's no distances. There's nothing. You're thinking about now and I have a vector, right?
The vector. Yeah, for example, if I have something يعني complex curvy, perhaps if I take something a little portion from here.
What is this? What is this? What are you talking about this? Yeah, but what are you talking about? You're talking about a vector between 2 points. But if you look at the points themselves.
The small local region.
And this local region has only points. It's a set. Egypt, this set that has Egypt has a point called Alexandria, a point called Cairo, point called
similar, but coming from different regions.
Yeah.
The manifold. So
they have an overlap region or not? Then there's no need to talk about them. There's no overlap. That's exactly the point of Muhammad. One maps has a map over is a subset over Greece. Another one is over Egypt. There's no overlap between them. You cannot do any comparison between them. You cannot talk about each one has just all of the points that includes Egypt, and the other one has all of the points that includes Alexandria. That's it. We're talking about sets here. Okay, so that's why we can talk about bijective maps. Yeah, makes sense. Okay. Any question? Make sense so far? Okay. Let's introduce, I wanted to give you an example, but we don't have time to do that. So let's introduce one more important definition, which is actually maps between manifolds. Let's say that we have a map that takes me from manifold M to manifold N. Okay. Can we say anything about the differentiability of this map? Yeah, can we say it's differentiable, C0, C1, C infinity? This one is a map, right? We can always map this with some phi, okay, phi M to Rn. And this will be, and this we can always map it, not this one, we can always map its, a subset of it. Here, we can always map this to another phi, maybe phi N. That's another set of charts, which could be actually from Rm to Rn, completely normal. And this is a map here. So this is a map that goes from, how can we define this? This is, so this, let's see, from here, so it's phi M inverse, and then F, and then phi N. You all agree? So I need to go first like this, and then like this. Yeah.
Okay.
So now this is a map from Rn to Rm, and now we can talk about differentiability and so on and so forth. Okay. So there is a very special type of name for maps that appears a lot, and you'll hear this name again and again. So we call F a diffeomorphism. So this is the definition. We call F a diffeomorphism if it is smooth, so it means it's infinitely differentiable. And the set of, so it's something I forgot to mention here, that the set of all functions F, okay, that go from M to R usually has this name. It's usually we say that F lives in CK over M. So this is actually CK of M is the set of all maps that eat the manifold and go to R of class CK. So taking this definition, we can call this a diffeomorphism if F lives in C infinity of M, but not only that, and also F inverse exists. So we're talking about the other map that goes from here to here. If it exists, and F inverse lives in C infinity of M. So this is what a diffeomorphism is. We introduced this. What does this diffeomorphism remind you of? We did something like this for sets, for groups, and for vector spaces. Where does this live? Or what does it relate to? Bijections between sets. What else? Linear maps between vector spaces, linear isomorphisms between vector spaces. And we don't have a notation, we don't have any notion of linear maps between groups. What was the name? Group homomorphism means that it's not bijective. If it was bijective, what would you call them? Group isomorphism. No, group isomorphism. Group isomorphisms was the notion we used. So we had bijections between sets, and we had group isomorphisms between groups, and we had linear isomorphisms between vector spaces, and now we have diffeomorphisms between diffeomorphism between manifolds, exactly, between manifolds. So this is just a conclusion. Okay, so the summary that when you have a set and you have a bijective map, okay, so between S and map T, then we call this a bijection. So this is the bijections. If you have a group G that goes back and forth, and the group G here, of course, it has its own operation, and it goes between another manifold, so another group that has another operation. We call this F, we call it a group isomorphism. And then when we had vector spaces, which are the V, of course, there was also the field, and it went back and forth with some other W. Then we call this linear isomorphisms. And now the new object that we have is actually a manifold M. And we have maps that go from one manifold to another. And we call them diffeomorphisms. What was the extra structure that a manifold needed, that a set needed to have to be a manifold? It needed to have, where was the shards? We put them in what? In the atlas, exactly, in an atlas A. So this has an atlas, let's call it AM. And of course, the other manifold will have an atlas of its own, AN. What else was missing here? This topology, stuff that we never talked about, okay? But it's still, it's there. So this is a topology on M, and this is a topology on N. So the triplet here is what's called a manifold. So this is a manifold. A vector space, a group, and a set. You see what I told you earlier, that a set has no structure. You can only talk about points, and that's exactly the same your point, Muhammad, right? When you said if I have a subset that has a number of points, I cannot do anything with them. If I have a group structure, I can start taking these points and I can multiply them together and get another point. I can have an identity element, which is a unique, a unique point on this group. I can have the inverse of some element and so on. If I have a vector space, I can take two vectors and add them to get another vector. I can scale the vectors bigger or make them bigger or smaller. But if I have a manifold, I cannot do any of this. I can only talk about why is this very important? Because I can talk about now what? No, I had also maps earlier. What? Differentiability, exactly. We can talk about differentiation. I can take differentiation with respect to time. If you want to talk about differential equations, I can look at sequences, for example, if you want to do optimization and stuff like this. So this is the structure that we need to have. But if you have a manifold, does this mean it has a vector space structure? Usually not. Could you have a manifold and a group at the same time? Yes, and what did we call these? We call these two go together. Very important. They are called Lie groups. And there's the last thing that I'll wrap up with is that we said that if we have a bijection between two sets, we called S isomorphic to T. And we had G, we said it's isomorphic to H, if we had this group isomorphism. If we have a linear isomorphism, we call V and W isomorphic to each other. And if we have the manifold, exactly the same. We say that M is isomorphic to N. Of course, the isomorphism here is completely different. We use always the same notation. I'm going to suppress now the subscript that we added before. So here this was as sets, and this is as groups, and this is as vector spaces, and these are as manifolds. But now you see the structure.
We can deal the differentiation here in this manifold. If we take the derivative, for example, on something from here to here, the result, can we make it as a vector space?
Sorry, again, what's the question?
For example, here, if we take derivatives.
If we take derivatives from here to here, okay.
This is a manifold.
If you have maps, only maps from F, from here to here. Derivatives are something else. We did not talk about them.
There is differentiation between defining the maps.
Next lecture, inshallah. Next lecture. So actually, we're not done yet. So you had a lot of questions this time. So you actually took time than what you're supposed to. So we were supposed to start next time with topic number 2, which is talking about rigid body motion. But I think there is some very important discussions we need to finish up, which is actually tangent spaces. And these actually tangent spaces are related to the differentiations of F. So actually, we're gonna have So sorry to inform you that we're gonna have one last lecture, on topic number 1. But hopefully, things we're gonna have. I'll try to make it with some mathematics that you can actually practice. We did not talk about them yet. We did not talk about tangent spaces yet. But this will be next time. So we still have some more work to do, inshallah. Any questions? Okay. Jazakumullah khair.